Hello, everyone, welcome back. So today we want to talk about one-to-one functions and inverse functions. So our goals first, be able to determine whether or not a function is one-to-one, explain what that means, also be able to see whether it's one-to-one using what's called the horizontal line test. We'll do this for the graph. Then understand the connection between one-to-one functions and inverse functions. As we'll see, for a function to have an inverse has to be one-to-one. Then finally be able to find the inverse function of a one-to-one function. So first, let's explain what a one-to-one function is. So a function f is called one-to-one if for any values of a and b, the domain of f, if a equals b, then f of a does not equal b. That's the mathematical definition. What that means practically is essentially is no y values repeated. Okay, so no function, no x value, different x values can never give you the same y value. That's what that means. Now, the best way to determine that from the graph is use what's called the horizontal line test. So if a horizontal line intersects a function in more than one point, the function is not one-to-one. Let's come over to the right, look at some examples of that. Now, you may remember from functions in general, the vertical line test tells you whether or not something's a function or not. So this tells you, we're starting with something is a function to begin with, using the horizontal line test to determine whether or not something is one-to-one. So we're going to draw a picture of a graph. I'll do a couple first. So let's say we have a graph that looks like this. How about just a straight line? Okay, where here is A and here is B. Then this point right here, of course, this is f of A. This is y. You plug in A, you get f of A. And here is f of B. You plug in B, you get f of B. You get the y value for that one. Okay, and this one is one-to-one. I'll just use numbers, one-to-one. Since, and this is true for any values on this function, not just these two. So let me draw a straight line here. Since f of A is not equal to f of B, not just for these two, but for any values. Okay. Now, let's look at one below, or I'll just do it over here. Let's look at another graph. How about this time look at maybe a parabola. Okay. And let's say this is A and this is our f of A. And let's say this is B. If you notice now, we have the same. This equals f of B. Okay, make that a little bit better. So this is first one's f of A, and then it's f of B. So the point is they both share the same y coordinate, both these two different points. Okay, so this one is not one-to-one. Since f of A is equal to f of B. And that's true if it's, and this is something's not to one-to-one if that happens at any point. As you can see, that's true for most points of this graph. It's not just true for these 2 points, but any other point, the other points where you have the same y value of any two different x values, that's called not one-to-one. And that's where the horizontal line test comes through. If I draw a horizontal line through this graph, then we say it fails the horizontal line test. Okay, which is not true over here. If I draw a horizontal line through this graph at any point, it would only contact it once. This one contact it once, or if it's more than once, it doesn't have to be anytime more than once. It could be 3 or 4 places. Okay, some graphs you would cross the horizontal line might cross the graph 2, 3, 4 places, maybe an infinite number of places. Just has happened more than once, so it's not one-to-one. Now, but as we'll see, parts of graphs could be one-to-one. For example, if I divided this parabola in half, then either half would be a one-to-one function, just not the whole thing. Okay, let's look at a couple more examples. And here, instead of graphing them here, we'll look at Desmos. Help us out. Let's say number 1. So what if we have f of x is equal to negative 2x plus 1? Okay. Now, This is a linear function. Let's graph it. So go to Desmos. There's dsmos.com. We'll just do y equals negative 2x plus 1. And clearly, this function is 1 to 1. Okay, draw a horizontal line through it anywhere, it's only going to touch it once. So it is 1 to 1. So it passes the horizontal line test. Okay, and so it is 1 to 1. All right, now what about another one? Let's do a couple that are similar. So this time let's do this. So our f of x is equal to x squared plus 1. What kind of graph is this? This is quadratic. This is a parabola. And I think we're going to guess, as we'll see, it's not 1 to 1. Okay, so x squared plus 1. Turn this one off. So y equals x squared plus 1. See, clearly this is one is not 1 to 1. Okay, because I can draw a horizontal line through many places. Every place except the very bottom here is going to cross it more than once. That's not 1 to 1. Okay, now, so it fails. It's called the vertical line test. Okay, and it's not 1 to 1. Okay, however, let's change it just a bit. Let's say the same function squared, x squared plus 1, but let's say we're just looking at x greater than or equal to 1, or could or not 1, 0. Okay, let's say cut the parabola in half. Okay, so what we have here then, go back and look at our graph briefly. So just this half right here, starting at 0, this half, and we also do either half. But if we do either half, then if our graph looks like this, okay, you can imagine drawing a horizontal line through it anywhere, and this one will pass the vertical line test, or not the vertical, rather the horizontal line test. Okay, so this would be or is 1 to 1. And that's what happens in many cases when you need to, maybe you need an inverse function for a particular function, this x better, then sometimes you may have to just do part of a graph. This is true of the graphs of trig functions like sine and cosine and tangent. Those of you who've seen those may take classes of those in the future. As if you see those graphs, you'll see those are not 1 to 1. If you take parts of them, some parts will be 1 to 1. You can use that. Okay, that's why I tell something is 1 to 1. Now, why does this matter? Well, we need a function to be 1 to 1 to create an inverse function. So let's look back over at the left. So if a function f is 1 to 1 with a domain A in range B, its inverse function, right, is f negative 1, and also this is not a power, this is the way its inverse function is written, is also a 1 to 1 function, and basically it trades domains and ranges, as this shows down here. So if you start with a function f, it takes the number A, transforms it to B, and this is the domain of f and the range of f. An inverse function does the opposite. It takes B and turns it back to A. Okay, transforms it back to A. It undoes f. And basically, either one can be the inverse function. They're both inverse functions of each other. We call the bottom one here, if we call that f, this will then be f inverse. So these functions undo each other. So a few things. It says that if f of A equals B, then f inverse of B equals A. So that's just what this idea of graphs undoing each other. Okay. Then also points on the graph, they switch x and y coordinates. The point AB is on the graph of f, then the point BA is on the graph of f inverse. Okay. Also, if we plug a function into each other, plug functions into each other, it's a composite function, f of x into f inverse gives just x, what you started with. And the same way, the order doesn't matter, plug f inverse into f also gives just x. Once again, that's what I mean by functions undoing each other. Okay. A few more things, as I mentioned here, this negative 1 is not a power. This is not 1 over f of x. Just make sure you're clear with that. Okay. Superscript here indicates a function, not an exponent. And finally, the graph of f inverse of x is the graph of f of x reflected through or flipped over the line y equals x. Remember, y equals x is called the identity function. We'll see that in a moment. Okay. Now, why is this important to be 1-to-1? First off, or have an inverse to be 1-to-1. Let's go back to Desmos just a moment. Let's actually just go ahead and let me just get rid of both these graphs. Now, let's take a look at a graph that was have an inverse. Let's say the square root of x. So when we can do the square root is come out here and pick that. The square root of x. Okay, you've seen that graph before. Now, turns out, as we may look at one similar to this in the future, its inverse function would be x squared. Actually, let me start with something else. We'll actually do something like that here in a moment. But so let's say y it's important for be 1-to-1. Let's start with something that's not 1-to-1, which is just x squared. Okay. We know that's not 1-to-1. Now, why does a function need to be 1-to-1 or to have an inverse? Well, as just said, the graph of the inverse function is the original function flipped over this line, y equals x. If I do that, and actually if I flip this line over that line, what I get is a parabola, which would be x equals y squared. As you can see, the problem with this is now this is no longer a function. This black line actually fails the vertical line test. It's not a function. That's the reason why a function has to be 1-to-1 to have an inverse. Now, as we said, if we took either half of this parabola, the green line, the green parabola, y equals x squared, that would be 1-to-1. You could have an inverse. For example, the inverse of this half here to the right of the origin would be this line, and the inverse of this half here would be this line right here. Okay, so half a parabola can give you an inverse, or even other parts of it, but the whole thing can't, because anything that's not 1-to-1, if you find its inverse, will no longer be a function. That's why that's important. Now, let's go back to what's next. So let's talk about some of those details of inverse functions. Let's see, I think I have, where is that? Here it is. Okay. I have something here. So this is an example of, get rid of that. Okay. Let me move this up. So here is a function in table form, and we'll work with this a bit. Here we're looking at, let's draw a line to separate this. Now we're looking at inverse functions. Okay. Let's start with this example. Okay. We have this function. Okay. Y equals f of x. This time it's in the form of a table instead of a graph or an equation. All right. Let's look at a couple examples from this. So if you can see from the table, for example, f of 1 is equal to 2. Okay. You plug in 1, you get 2. And what that means then is, from these statements here, if f of a equals b and f of negative b equals a, what that means then, if I go backwards, f inverse of 2 will give me back 1. Okay, let's pick another one. Let's say, how about f of 1, f of 4 is equal to 6. Then, excuse me, then f of 6, if I plug 6, sorry, what's going on here? Okay, let's try that again. Then f inverse of 6, if I plug 6 in the inverse, I get back what I started with, I get back 4. So I'm going this way. So f of 2 was 1, then f of 6 is 4. Okay, so in the same way, if I simply start with just the inverse function, if I just say number 3, if I say f of 1, well, sorry, f inverse of 1. So in my function here, if I plug in x, plug in 5, I get 1. So if I go backwards and plug in 1, I get 5. I'll say since, this is true, since f of 5 is equal to 1. Okay, that's how inverse functions work. Okay, so for example, also, this is the domain of f, the function f, and this is range. So if f inverse, its domain is this, and its range is that. Okay. Now, also explain a bit more about the idea of inverse functions. So it said inverse functions undo each other. So imagine, one way you can imagine this is imagine maybe a kind of, this may not be precisely right, but kind of gives you an idea. Okay. Imagine a snack machine. So you put your money into a snack machine and you get out, whatever you want. Okay. Or a drink machine. Let's say immediately you get it out and you decided, well, I didn't really want that. Imagine there's a machine right beside it where you can put that drink or that snack into the machine and get your money back. That would be essentially an inverse function. They'd be inverse of each other because basically you get back what you started with. They undo each other. That would be the idea of an inverse function in a sense. Okay. Now, let's explore the idea of the inverse function graphically a bit more. So I think I can probably move this up here. I have a graph I want to take a look at. Let's see if I can get it up here. No, I think I'll just bring it back. Let's make sure I have enough space. So when we look at this graph, here's the graph of our function f of x. Okay, what we want to do then, you want to draw f inverse of x. Okay, y equals f inverse of x. So what we said is that we take, this is our line y equals x right here. So to get the inverse of it, you flip this graph over this line y equals x. And also our points here, our points will switch. Notice this point here is 2, 4. This one is 0, 3. And this point down here is -4, -5. So this also what this says, points, where did I say that? Yeah, if the graph of fx goes to the point AB, then f inverse goes through the point BA, switch it, okay? So the inverse function will go through the point 4, 2. No, I did that again, sorry. 2. Okay, this point here, the original graph is 0, 3. So the inverse, it will be 3, 0. And this point here, which is -4, -5, its inverse point is then -5, -4 right here. Okay, so the graph of the inverse then looks like this. If I can draw a straight line from here to there, and then that. That's a graph of y equals f inverse of x. Okay, also one more thing quickly on this one. So for y equals f of x, let's also think about the domain and range. So our domain of f, the original graph, it goes from -4 to +2. And both those points are included. And its range goes from -5 up to +4. And both those points are included. Now, so you can see this, and this is also what this statement here says, that basically the domains and ranges switch. Okay, what this graph says. So the graph of y equals f inverse of x, its domain should be the range of this one. Okay, we'll check that. So -5 to 4. So make sure that's right. Right, it starts at -5. It goes to +4. Good. And its range should be the domain of the original function. And that should be -4 to 2. And once again, we'll double check that. Right. Goes from -4, right, up to +2. Good. And also, once again, this is true. So if this function here had been the original function, if this had been the original f of x, then its inverse would be this. They're inverses of each other. There's not one preferred over the other, both inverses of the other function. Okay. So those are the ideas of inverse functions. Okay, so remember, graphically, the line is flipped over this line y equals x. Points switch coordinates. Okay, and then also remember they undo each other. All right, so now next thing I want to take a look at, and let's come back over here to the left, is talk about being able to find inverse functions. Let's talk about the procedure to do that. So we want to be able to find a function, inverse function, given another one. Okay, so we have a procedure for that. We'll go to the left. It says, starting with the equation of a one-to-one function. So first, make sure it's one-to-one. We can graph it and find out. Use the following steps to find the inverse of f of x. So let's go ahead and start with our first example, and then we'll kind of go through the procedure. And give me a moment. Let me get to the examples I want to do. Okay, so number one, let's say we have f of x is equal to, let's say, negative 2x minus 5. Okay, now first off, is that one-to-one? Well, we can graph it and find out. Let's do that. Let me get rid of these. So y equals negative 2x minus 5. Okay, right. It's a linear function. Clearly, it's one-to-one. And actually, the only linear function which won't be one-to-one will be a horizontal line. So keep that in mind. Okay, so clearly it's one-to-one. Now, how we're going to do this? Okay, so let's kind of know these steps. So step one, it says replace f of x with y. Okay, I'm just going to call this y, which you can always call it y anyway. We'll do that here. So y equals negative 2x minus 5. Okay, now step two. Okay, interchange x and y. That means replace x with y and y with x. So here's y, and make this x, and then here's x and make this y. So x equals negative 2y minus 5. That's step number two. Now, in step number three, this is kind of where the main work is, solve for y. Okay, so from up here, I want to solve for y. So I want to add 5 to both sides. So I have x plus 5 is equal to negative 2y. Okay, then divide both sides by negative 2. And that's going to give me, I'm also going to turn this around, y equals x plus 5 over negative 2. And of course, we don't really want to leave it like that. Let's make it look at it as a line. And so this is going to be, I can divide this. If I can show this step here, I can divide this, make two fractions. And so this can be negative 1/2 x minus 5 halves. Okay, so this is my inverse in the last step, number 4. This is just replace y with f inverse of x. So finally, my inverse function is f inverse of x is equal to negative 1/2 x minus 5 halves. Okay, so let's make sure that's true. So let's go back and graph that. So first of all, so here's the line y equals x. Okay, so it should be flipping it over that line. Let's see if it does. So once again, remember that was y equals negative 1/2 x minus 5 halves. Okay, yeah, and I think it clearly looks like that. Now let's double check that. Let's look at a few points. Okay, so back on the red line, let's look at intercepts. So here's one at 0, negative 5. That point should be mirrored here, and it is negative 5, 0. The intercept for this green line is 0, 2.5. This point here should be negative 2.5, 0, and it is. So that is our inverse function. Okay. And so what that means is if I plug a value into this, right, let's do that. So let's do f. Let's try this on this one. I'll just say, so if we do f of 1, let's pick something simple, f of 1, this is negative 2x minus 5, is going to be negative 2 times 1 minus 5, and that's going to be negative 7. F of 1 equals negative 7. Now, let's see if this works, okay? Then we should get back, we plug this into the inverse, it should be 1, okay? If I do f of negative 7, okay, into this, negative 1/2 times negative 7 minus 5/2, okay? Now, remember fractions multiply across, and so this is going to be positive. It should be negative 1 times 7 is positive 7/2 minus 5/2. Combine those, and that's going to be, combine our numerators, that's going to be 2/2, which is 1. Right, and that's what it should be. So we plug 1 in a number in the first fraction, we got that value, plug that value back in the inverse, then we got what we started with to begin with. So that is definitely the inverse. Okay, let's look at a couple more examples of that. Also, let me check and see what page I'm on in terms of my notes. Okay, it should be, I believe that should be enough. Okay, number 2. This time, let's do a, I think I mentioned this before, let's do a square root. So let's do square root of x minus 1. Okay. We'll follow these same steps again. So step 1, call this y, replace the fx as y equals the square root of x minus 1. Then step number 2, switch x and y. So make this x equals the square root of y minus 1. Then step 3, and sorry, I should have done something first. Let's go ahead and make sure it is 1-to-1. As you can see, this is a good habit practice to be in. Let me get rid of these. Okay, so y is equal to, you also do square, just SQRT, and then x minus 1. Right, so that function is 1-to-1. Okay, it's always good to check that to begin with. Step 3 is solve for y. All right, so if you remember how to do this in this case, this is essentially a radical equation. So the way to get the y out of the radical is to square, in this case, square root. So square both sides. And what we'll see is there's actually something that happens when we do that. Okay. And so now we have x squared. And remember, since these are in, it's also a case where these are, the square and the square root are also inverses of each other, so they cancel each other out. So we square a square root to get what's underneath, which is y minus 1. Then just add 1 to both sides. Then we have y is equal to x squared plus 1. I believe you've even seen that graph before. All right. Now, one thing you have to be careful with, we're not quite done. Okay, so let's see what's happened. We graph this. Let's go back over here. All right. Let's also graph the line y equals x. Now we said it should be this graph flipped over that line, and we said it should be y equals x squared plus 1. And if you notice, we get a full parabola. And this is actually kind of a graphical way of seeing what happens in general with radical equations. Why, if you raise both sides to even power, you have to check your answers, because you saw we started with this and we got the full parabola. We started half a parabola, filled on its side, we got the full parabola, okay, which isn't what we needed. But what we have to do then is decide, okay, looking at this, clearly the right side here, think about flipping this over this point. For example, this point right here is 5, 2, should be 2, 5. I can stop on it. There it is. Okay. So this half of this parabola right here is our inverse, but not the other half. So I have to make that clear. What I'm going to say is, well, let's do that down below. Okay, for step 4. Okay, and so what we need to say then is f inverse of x equals x squared plus 1. And then for x is greater than equal to 0. Okay, I'll say since only the right half of the parabola is the inverse. Okay, so in some cases you have to be careful with that, especially if you're raising both sides to even power, not a non-power, raise both sides to an even power. You have to watch out for that. Okay, last one, number 3. All right, this one, a little more work to do, but we'll can handle it. So f of x equals 8x minus 1, so like an 8, over 7 minus 5x. Okay, once again, first, let's graph that, make sure it is 1 to 1. As you see, it is. So let's get rid of all these. Now, also how to do a graph like this in Desmos is make sure you use parentheses, but start doing this. If I do 8x minus 1, then divided by something, we'll only divide the last number by that. So use parentheses. So 8x minus 1, close the parentheses, then we can divide it by 7 minus 5x. Okay. Now, this is 1 to 1. Maybe it's hard to see that, but basically these lines here are approaching an asymptote, which is actually going to be, actually graph that. And if you've seen my video, another video on rational functions, basically it's going to be 8 over negative 5, or negative 8 divided by 5. It approaches that line, but it never reaches it. So this function is still 1 to 1. Okay, because it never reaches that line. So it's never horizontal. So it is still 1 to 1. Okay. Now, so let's talk about how to do that then. We'll do the same 4 steps. Be one more to solve. So step 1, okay, is once again we want to just call this y equals this 8x minus 1 over 7 minus 5x. Okay, step number 2, switch your x and y's everywhere. So now x is equal to 8y minus 1 over 7 minus 5y. So switch x and y's wherever you see them. Okay, now actually let me make sure I have enough space here. Okay, now step 3 is once again where the work is. We're going to solve this. Solve for y. Okay, now if you remember, hopefully you've seen, this is basically a rational equation. Hope you've seen how to solve those. So basically what you want to do then is you want to essentially find the least common denominator. If you have variables denominator, that denominator is the only denominator, will simply be 7 minus 5y. Okay, and now what I'm going to do is multiply both sides by that. So I have 7 minus 5y times x is equal to 7 minus 5y over, or times the right side, 7x minus 5y. And you see the reason we do that, this cancels this out, and we're left without denominators. Okay, so now over here, then obviously we have 8y minus 1. And the question is maybe what do we do over here? So eventually I want to get y by itself, but y is inside this. So the best thing to do is distribute x times each one of those. And so that's going to be 7x minus 5xy. Okay. Now what we want to do then is get the y terms together. Doesn't matter which side. Okay. I think I'll get them, let's see. I think I'll get them together on the left side. So, or I want to do them on the, let's do on the right side. Let's add 5xy to both sides. And in doing that, if I'm get the y's over here, I want the constants over there, so add 1 to both sides. Okay. That crosses out, that cancels out. What I have now is on this side, 7x plus 1. And over here, I have 8y plus 5xy. Okay. So we're a little bit closer. Now we have the y's on the same side. And so how can I get the y's out of this? Well, in the same way I distributed here, I'm essentially going to do the opposite of distributing. I'm going to factor a y out over here. Okay. So take a y out. of both of these, what I'm left with is 8 from this one plus 5x from this one. Okay, this side, the left side is still the same for now. And then I just have one step left to do. Divide both sides by 8 over 5x, or 8 plus 5x. Divide both sides by that. This cancels out over here. Also, just turn this around, and y is equal to 7x plus 1 over 8 plus 5x. And then the last step, I guess I go ahead and go down here. So step 4 is just replace the y with f inverse of x is equal to 7x plus 1 over 8 plus 5x. So now let's make sure, let's graph that and we convince ourselves it is the inverse. 7x plus 1 over 8 plus 5x. Y equals x. So that was 7x plus 1 over over 8 plus 5x. Sorry, 8 plus 5x. Okay. Now that kind of looks reasonable. Let's see. Let's go to the black graph. Let's see what this point right here is. Okay. See if that matches that. A little hard to see, but let's zoom in on it some. A little far out. Okay. Yeah, let's look at these points here. That's probably best. So our x and y intercepts here, and those should be matched by our x and y intercepts over here, except just reversed, coordinates reversed. As we can see, that is. So here, the coordinates reversed here. The y-intercept is the x-intercept of this one. The y-intercept of this graph is the x-intercept of reversed is the x-intercept of that graph with the coordinates reversed. As we can see, pretty clear that over the purple line, which is y equals x, that's that graph flipped. So that is the x-intercept. That is the inverse function. And also, once again, the inverse, if you did the same thing here, you started with this and did the same 4 steps that's driven in the rest we've done, you would get this for your inverse. Okay, so let's review what we've talked about today. So we introduced one-to-one functions and inverse functions. So remember, one-to-one function has to pass what's called the horizontal line test. If a horizontal line goes through it more than once, it's not one-to-one, and that means y is repeated. Now, so to have an inverse function, the function has to be one-to-one, and often you can make it part of it. Part of it often will be one-to-one. You can always use that part if necessary. And then we learned some of the details about one-to-one functions. We learned that the graph of a one-to-one function, if a graph of a one-to-one function is inverse, is the graph of that function flipped over the line y equals x, and x and y coordinates switch. Then we learned basically the 4 steps used to take a one-to-one function and then to find its inverse. All right. Thank you. Have a good day.